This video will look at the solution of Edx M2 June 2011 question 5, and the question is on the topic of work and energy. So here's the whole question, but it's effectively in two parts, which I put onto separate pages so that we've got some room to work around it. Basically the question is about projection of a particle up a slope. The first part involves a smooth slope, but part B brings in friction and therefore work done against friction. So let's look at the parts in detail. For the first part of the question, I'd like to pause the video to just read this carefully first. We've got a particle starting with an unknown speed, which I'm calling u, at the bottom of the slope at A, and passing through B with a speed of 5. And it's a smooth part of the slope, so there's no friction from A to B. So because there's no external forces other than the weight doing any work, the reaction does no work because it's perpendicular to the direction of motion. What we call mechanical energy is conserved. In other words, kinetic energy and gravitational potential energy, the total is constant. So using that idea that I've written in green, we can just come up with this simple equation, that a half mu squared must equal a half mv squared at the top of the slope at B plus mgh. And there's no need to bother to put the masses in because they'll cancel out, and we can double things as well. So u squared will equal v squared plus 2gh. Now we know v squared, so I can put that in. U squared equals 25 plus 2 times 9.8, and the vertical height difference between A and B, as you'll see from the triangle I've drawn on the diagram, is 2 sine 30. So now just push the buttons on your calculator and you'll find that u comes to 6.7 meters per second. That's the initial speed at the bottom of the plane. On to the second part. Now the second part involves the particle P coming to rest at C, which is further up the plane from B. In fact, it's 1.5 meters up the plane from B. And remember, it had a speed of 5 at B. So this time there's going to be energy lost against friction. And if we can write down the work energy principle in general terms here, we'll have the kinetic energy at B. Where will that kinetic energy go? Well, it'll turn into the gravitational potential energy at C, but some of the energy will have been lost against friction. So plus the work done against friction. Now, to deal with friction, let's use this space here. We know F will equal mu r, friction equals mu r. And also, if you look down in the bottom corner here, you'll see it's easy to find r because we can resolve perpendicular to the plane, and r is simply 0.5 g cos 30, mg cos 30. I think I'll call that mg cos 30. It'll make life easier if I just call it m. So, putting the terms in my energy equation then, the kinetic energy at B is a half m v squared, which is a half m 5 squared, is equal to mgh, which is mg times 1.5 sine 30, plus the work done against friction. Now that'll be friction times the distance the particle moved against friction. So it'll be mu r times 1.5. So mu mg cos 30 times the distance, which is 1.5. Now the m's will cancel out of that equation, and then it's time for the calculator. So 12.5 equals 7.35, check that you get the same numbers, plus mu times 12.73, which gives us mu equals 0.405. And that's it. As far as marks for that question is concerned, for part A, there was an M1A1 for this statement about the conservation of mechanical energy, and then an M1 and an A1 for putting in the correct values and getting the correct answer. So 4 marks for that part. And for the second part of the question, there was a B1 for stating the value of R, and an M1 for using F equals mu R. Then there was an M1A1 for the energy statement there, another A1 for putting in the correct values here, and a final A1 for the final answer. 1, 2, 3, 4, 5, 6. That's right, 6 marks for that second part of the question. And that's it. So thanks for listening. I'll just leave you with some information about the Further Maths Support Programme.